Is Jim Wyatt still coming around some of the time?
Sometimes, yeah.
Okay.
Yeah, I don't know if you ever
No, it's him.
Still doing okay, but it's really hard.
Okay, no, I'm not. Right, yeah, sure. I can understand that.
I'm actually going to see him tomorrow.
Hey guys, today we have Dr. Paul McManamon. He's our nation's best Lidar active imaging person. I met him, I don't know, 25 years ago.
A long time ago.
It was a long time ago, but he was chief scientist of the Sensors Directorate at Air Force Research Lab at that time. He's written all the books on active imaging. His latest book is on Lidar.
Yeah, that won the Goodman Award too. I'm very proud of that.
This was the Goodman Award, which is
most of you know who Joe Goodman is because he was taken for Optics. Although
he's a Goodman chair,
I
you
know.
He knows.
yes, okay.
And he knows no.
But actually, who was it? There's another book that is on Fourier optics. Somebody here wrote that. I forget who.
Jack Gaskill.
Jack Gaskill. Yeah. And that book actually does better on the electrical engineering side.
You guys, I'm going to give it to Paul, but he's a past president of SPIE, overachiever, has accomplished more than most of us will ever dream of. So with that.
But thank you very much. Yeah, I retired from the Air Force now. It's been 2008, and my wife tells me I flunked retirement, which I did. Because the problem is all this science stuff is so much fun. If I really enjoy doing it, and sometimes people pay me, why wouldn't I keep doing it? And so I do. Just a few little odds and ends. He already showed you. There's my book, which is a tutorial. This one's a field guide. Here's a bunch of cards if anybody wants them. They're cards from my company, Exciting Technology. I've got cards from there and from the university and this other little company that wants to 3D map the world. And then, just in case, since I have 5 grad students at the University of Dayton, I brought along some University of Dayton things too, just in case anybody wants them. And I'd say, in LiDAR, I agree with you. I think I'm the best. I'm humble too. I also would say that in optical beam steering, since the mid-'80s, I've wanted to steer optical beams with no moving parts. And we've made progress. I'll say in a minute how we've done sort of a breakthrough there. We are pretty good in free space laser comm. I've got a group of people doing that with the Navy next week down in Charleston. There's other folks who are good in atmospheric optics at UD as well. So in any event, I'm going to mostly talk about LiDAR. But I'm going to also talk about, up front, I'm going to give you just a little snippet of some of the other things we're doing. LiDAR, free space optical, these are some of the things I work. Optical beam steering, crystal growth. We're trying to do high-speed modulators. This is with the university hat. Nanolin in China has worked with Harvard and done a 100 gigahertz modulator, which is really neat. There's people here who would rather have that in the United States. So University of Dayton is working with Ohio State and with Gooch and Houseco, formerly Cleveland Crystal. We would like to bring that capability into Cleveland, basically. And I'm working alternate materials besides lithium niobate and directed energy some. And let's see. Okay, I said a minute ago that I've been working on optical phased arrays for a long time, and I have. The problem you have with optical phased arrays, just to give you a background how optical phased arrays work, or how any phased array work, you're going to go like 0 degrees, 30, 60, 90. You go up to 360 degrees, and then you do a 2 pi reset or a 360 degree reset. You do that because if I want to write a prism here, and let's say I want to steer to 30 degrees, and it's a 10 centimeter aperture, that would say I would need an optical path delay of 5 centimeters right there, which is a lot. If I can get by with an optical path delay of 1 wavelength, it's much easier. So that's the way, generally, phased arrays are not true time delay phased arrays. They're modular 2 pi phased arrays. Somewhere in the early 90s, I discovered when you're doing space-fed optical phased arrays, there's this problem called fringing fields. I was a government guy at the time. Raytheon was working for me, and they made a 40,000 electrode device, which was on 1 micron center-to-center spacings. And we discovered that if you put a high voltage here and a low voltage there, that the D field didn't change right away. It basically, though, the width of this is about how fast in this direction the E field can change. And that's a fringing field problem. Now, in addition, liquid crystals also have a spatial order problem. Long, skinny molecules like this don't like to sit next to long, skinny molecules like this. So if you beat the fringing fields, if you're using liquid crystals, then you still have a problem because of spatial order. So what happens, and we discovered this in the early 90s, is that instead of having it go straight up and then down like you want, like this, it would go straight up and then it would sort of wander down. And this part here is steered the wrong direction. So I spent 3 decades trying to figure out how to beat that. We figured out how to beat it. This is a COMSOL run showing, and this is 20 degree steering, but this is a COMSOL run of the near field, and that's all I'm going to say about this because I've got too many topics to talk about. There's another thing that's pretty interesting. I was telling Ron a little bit before that as far as free space, that we have a novel mechanical beam steering approach, which can steer and magnify at the same time. There's some people who tell me you can't do that, you're beating a conservation law because when you magnify, the angle is supposed to go down. But we've done it in the lab, it works. But the other interesting thing about this is we can do multiple beams through the same spot, through the same aperture at the same time. So coming out of here, you know, I could have a bunch of movers here. I could have 7, I could have 19, I could have 37. The angles get a little smaller, but I can steer multiple beams through the same aperture at the same time. If you're doing, say, laser comm, and you would like to talk to 12 different people, other people would want 12 apertures. We can do it with 1 aperture. And we can independently steer each one of those, which I think is pretty neat. This is a laser vibrometer. That's something we just built recently. That was through my company. 64 by 64. It's short range. It's a lab instrument. I think there's a good chance we'll get to make a 1.5 kilometer instrument, which would allow us to really just do a lot more in order to collect data and stuff like that. That actually is in the laser area. This is free space laser comm. We're doing 10 gigabits per second, low size weight. We've done it in the lab, both off a Colloquium and with independent units on each side. Till recently, we were going off a Marriott out this window. It had a Colloquium, on the other side. And rather than, and just recently, we got we've got 2 units, so we can actually take the other unit out there, which we're probably doing today. The reason why we did that is because we're going down to a Navy exercise next week. And this contract doesn't require us to do this till next May, but we wanted to catch this Navy thing, so we're catching it. This is, as I said, this is the device. This is one of the little decentered lens type gadgets that steers plus or minus 20 degrees. Right now, he's only saying plus or minus 10 because we bought cheap lenses, but we can do plus or minus 20. But, that's at 1550, but it could be at others. That it could go through. And the other thing is we're working with MZA. Some of you might be familiar with MZA, but MZA is a company that really does atmospheric optics well. They're both in Kirtland and in Dayton. And they're setting up and characterizing the atmosphere. And we now are sub to them on an Army contract. We did this originally under an Air Force contract, but we're sub to them on an Army contract where what they want to do is they want to characterize the atmosphere, and then we can turn up and down our power and we can be adaptive. Now, you're not going to go through clouds. You get fog or something, we're not going to do that. But I think when you get turbulence, there's a lot of things we can go through, and working with MZA, we'll do the most you can. So I think that's really sort of neat. Okay, now, LIDAR. The rest of this I'm going to be about LIDAR just because I wrote 2 books on it. I chaired the National Academy of Sciences study on the subject. It's something that I do a lot of. And so I thought I'd talk about it. First thing I want to talk about is names, which is LIDAR, which is the one I tend to use now. LADAR, which some people use. Laser radar. I used to use laser radar. Then I would use LADAR for hard targets, and I would use LIDAR for soft targets. But then all the commercial space uses LIDAR nowadays. When I was an expert witness for Uber against Google/Waymo, the lawyers always wanted me. I'd say I use LIDAR, laser radar, and it always came out LIDAR with all of them capital except the I, because that's what the lawyers said was the thing that people liked and all that. That's another fun thing that if I had time, being an expert witness for them was sort of fun. I've got like 10 charts talking about the process of being an expert witness. I kept telling the lawyer guys that, you guys just slice the pie. We make the pie. we're much better than you guys are. But they were pretty bright. Actually, I didn't end up getting to testify. They settled mostly because I think we would have won. I was on the Uber side. I'm pretty sure we would have won. But the guy who was the lead lawyer for that was saying, I was really disappointed because I wanted to introduce you and say, and our expert witness really did write the book. So in any event, but that was sort of a fun thing to do. Actually, an interesting tidbit from that is, since I was on the other side from Waymo, I've had 36 people from Waymo sign up for my week-long short course. Most of them online. And when I brought a flyer along, if any of you can do it online. If any of you want to take a week of Lidar, then it'll be next June is when we do that. Ed Watson helps me some with that too. But in any event, and if radio detection and ranging. Oops. And this is from Google Ngrams, how popular the different things are. Now I swim with the tide. You can see that Lidar is way down here. There's different capitalizations. The other thing to think about, so where does Lidar or Lidar, whatever you want to call it, where does it fit in the electromagnetic spectrum? Why would you do one as compared to the other? Typically, if you're a radar guy, you might, for one of the popular bands is 10 gigahertz, which is 3 centimeter wavelengths. One of our popular bands is 1.5 microns, which is 200 terahertz. It's really funny. The optical people hardly ever say what the frequency is, and the RF people hardly ever say what the wavelength is. So you got to sort of match them in order to do that. It's just, but in general, I like Lidar more. And when I was chief scientist, I was supposed to love all my children equally, all the different sensors. I really like Lidar more. But the thing is, when I'm riding on a plane and I'm in clouds, I really like radar. I sort of like it if they know where I am and I'm not going to bump into another plane and stuff like that. So there are times when microwaves are better. I would say from a free space optical comm on the battlefield that you would like a combination. You really don't want our typical RF comm on the battlefield. You get on your radio, and within a minute they've done direction finding, and you get this thing called ordnance that's falling on your head, and that's a type of rain that really is not very conducive to living. And so I think you want to keep your RF very low, hiding in the noise, hiding in the clutter, and then when you got a lot of data, you do it with the EO. But we don't go through fog, so it don't work all the time. So they've got jamming and they've got getting killed. Both of which are non-optimum. We've got clouds, and so neither one is a full solution. But so this, we fit with the other thing I would say with optical comm with Lidar, that's 1.5 or 0.5. It's more like you're used to. What you see is more similar to what you'd see, with your eye. You've grown up seeing with your eye. And radar is very different. You've got these little corner cubes. In fact, I'll say that's better for me to wait a little bit. Why Lidar? Okay, EO is excellent real beam resolution, 20,000 times better. The signature looks closer to normal. We control the illumination, so you compare it to passive. You can do near IR at night, whereas we don't do near IR at night when you are doing passive, because you just don't have enough signal. There's night glow. There's a little bit, but it's not that much. And the other thing is we can detect the field. Detecting the field is really, really neat. I won't go into that too much here. If you take the course, I'll talk more about it. But when you detect the field, there's all these really neat things you can do. You can focus and defocus after the fact. You can remove aberrations after the fact. You can make large synthetic apertures. As I said, you can make large synthetic apertures, large being like this. A radar synthetic aperture is probably 5 kilometers or 10 kilometers, because of that difference in wavelength. And this is what I talked about, how things look more natural. This is a radar image taken at about 18 gigahertz with the link SAR from General Atomics. It's a near-as-9 image. That's a really, really good image. This is a really good image in the visible. So if you put a bomb down on something and you're being court-martialed because you screwed up and it was a truckload full of nuns rather than a tank, which image would you rather show the judge, this one or that one? If you're an analyst and you look at this, you say, oh yeah, that's obvious, that's an M60 tank, because an analyst knows how to do that. But for an average normal person, being more literal, being more similar to what you're used to makes a big difference. A simple LiDAR. What is a LiDAR? Well, you need a laser. Well, actually, you don't need a laser. The Soviets were doing laser radar, I wouldn't call it laser radar, LiDAR, in, let's say, 1937 with a really bright pulse source. But LiDAR really came into its own with the invention of the laser. And then you're going to have some sort of optics, and you're going to send it out. You're going to go through some sort of medium. Generally, it's the atmosphere. It could be water. That's another. But then if it's water, you want to be probably in the blue-green. You're going to bounce off a target, and then you're going to come back. You're going to detect it, and you're going to process. So the major components: transmitter, receiver, optical apertures, and beam steering and processing. Those are the major components for a LiDAR. This, to me, I think is an interesting chart. Here's a picture of a tank under camouflage. Here's a first return from a LiDAR, the tank under camouflage. Here's a second return from the LiDAR. You can hardly tell that the camouflage is there. We were flying over Columbia when they were doing all the drug labs, and it was fairly dense foliage. We could watch everything they were doing. If you've got 10% holes between the leaves, you're going to see through, and you can make a 3D image. And then you look from a different angle, and it's a different 10%. And in a little bit, you can build up a really good image of something that you see that's under trees.
Can you explain why you mean by first return versus second?
Okay, the first return is going to be off the first object it hits. It's going to be off the top. The second return, in this case, is going to be after, is going to be later. So the second return, I'm cutting this off, and I'm just looking at what you see that's below the first return.
This is like computing the image, or this is something?
No, it's measured. It's measured, but there's a question of what part of what you measured that you're viewing. In this case, you're measuring the things that came second rather than things, and you can do a whole range profile. You can do a range profile with 50 or 100, depending. It's more storage, but with 50 or 100 different spots. But that's one of the powers of the LiDAR. Yes.
What kind of time resolution do you need for this then? Because if the first surface is 3
Right.
meters away from the second
So-
surface, you're on 10 nanoseconds.
Okay, so I like to say that the speed of light is a foot per nanosecond. I mean, other people say 3 times 10 to the 8th meters and all that. But being a LiDAR guy, I like to say it's a foot per nanosecond, and it folds over. So, if you've got a nanosecond pulse, you should be able to get a half of a foot resolution approximately. So you do need to be able to separate those in order to see that. And you can do bistatic or monostatic. Bistatic says you've got 2 transmitters and 2 receivers maybe. Monostatic says you do it all out of 1 aperture. Actually, interesting story with that. For the auto LiDARs and all that, Google actually patented a thing for monostatic LiDAR. And I mean, when I at the time, I looked at that and was saying, well, that's BS. But what was really interesting is I read a few years ago, some engineer paid his own $7,000 to kill that patent because it just pissed him off so much. We'd been doing it for like 40 years, but the patent examiners didn't know what was going on, and in any event, they allowed the patent. Okay, if you do monostatic, your big problem is transmit-receive isolation. Oh, and let me go back and make one comment on this one too. Bistatic, I think, will become more popular in the future because you can do something called MIMO, multiple input, multiple output, where you've got multiple transmitters, multiple receivers, and the fact you can, and if it's coherent, and you can capture the field, there's all sorts of wonderful things you can do with multiple transmitters and multiple receivers. But you do have an issue of isolation. You don't want the reflections from your transmitter killing your detector. And polarization is one way to do that. Oh, when I moved it over, something changed there. Isolation, temporal isolation is fine if you're using pulses. If you're using CW, not so much. Okay, resolution and accuracy and also precision. Resolution is what you were talking about there. I've got 2 returns, and how far apart do they have to be before I see a dip and I can tell that they're 2 rather than 1? Actually, an interesting story, 20 years ago or something, I was out at Starfire Optical Range at Kirtland. And I don't know if any of you have heard of or know Bob Fugate, but he was doing adaptive optics there. And, we could see this image, and it's a big blurry image, and then they turn on the guide star, and all of a sudden you can see the two stars separated because the adaptive optics clicked in and they could do it. And they could do better than the Hubble telescope because they had a bigger aperture. But of course only when there's no clouds and stuff like that. Actually, I shouldn't waste it, but I got to tell one more story about Bob Fugate. He's a really bright guy. And as I said, he really did a lot of the adaptive optics. They did it in the dark for the Air Force. When they published it, it swept the whole astronomy community. But I got a chance to write a recommendation letter for him when he became a fellow of, not a fellow of AIAA. It was to get some award, to get an astronomy award from AIAA. And my letter was really simple. It was wonderful. It's, well, from my point of view, there's been two big breakthroughs in astronomy. The first was the invention of the telescope, where you go from your eye to a telescope. The second was adaptive optics, so you could go from a telescope this big to one that's this big. And I said, to my knowledge, no one's nominating Galileo for this award, so it's obvious Bob should get it. Okay, so then range precision and accuracy, they're sort of the same, except one knows exactly where you are in the world, the other doesn't. There, if you've got good signal and noise, all you're really trying to do is you're trying to see where is the peak. And the better your signal and noise, the easier it is to figure out where the peak is. What's the range resolution? It's C times the delta time divided by 2. Why is there a 2? Somebody, why is there a 2? Both ways, round trip. Yeah, it folds over. Yep. And then it's really a question of a convolution of the pulse and the targets. So if I've got a long target, my return is going to be wider than if I've got a short target. Okay, that's enough on that. There's another problem that you have, which is that they call this range walk, where I've got two pulses that are different amplitude. If it's just a threshold detector, the high amplitude one appears to be before the low amplitude. Now, if you measure when it goes up and when it goes down, you can tell that. If you can measure the amplitude and take the ratios, then you can get rid of range walk. But getting range, it's not a big error, but it is an error. Doppler shift, 2 times velocity divided by wavelength. If you're trying to do Doppler shift with a Lidar, remember that factor of 20,000 times between X-band? I get 20,000 times more frequency shift than the X-band radar would. So if you want to measure vibration, you want to measure fine motion, Doppler Lidar is really, really good. We can do microseconds, micrometers per second type of resolution, which is really, really good. And again, there's a factor of 2 in there for the same reason. Diffraction, lambda over D, but well, I tend to use lambda over D. There are a lot of people like Ed Watson who will tend to use 1.22 lambda over D. And that's from the middle to the 0. I tend to do full width at half max. That's the way the radar guys do it. Now, really, it isn't lambda over D. It's 1.03 lambda over D if you want to do perfect. I use 1.2 lambda over D a lot of the time because I haven't found that many people who give me perfect lasers. And so you put a little bit more in there. One of the guys that I used to work with who did lasers, his main thing is lasers are no damn good. They are something's always going wrong, whatever else. Okay. The eye safety, that's a big deal. So the reason why some lasers are more eye safe than others is because of water absorption. And when light hits the surface of the eye, then, if you're at 1.5 micron or 10 micron, you might burn the surface. But it isn't going to get all that magnification. It isn't going to go back and zap the cornea. Whereas if you're between 400 and 1400 nanometers, it will. It's a gradual roll-off. So that's why visible light can hurt you a lot more. Now, when you say it's eye safe, if it's a megawatt laser, it's not head safe. Your head is coming off. It's not just your eye that's going to be the problem. Actually, one other story I got to tell you from way back when. I wasn't in the room at the time, but I knew people who were in the room. The Air Force was considering laser designators. And so somebody brought up the eye safety issue. And you can tell how long ago it was because there was a full colonel sitting in the back who was smoking a cigar, which he'd never be allowed to do today. And he just breaks out laughing. And he says, "You mean to tell me you're worried about blinding this poor, dumb son of a bitch, seconds before a 2,000-pounder goes off in his lap? I think you should worry more about the," and it's at that end of the discussion. When you're doing a designator, you're pointing it there in order to have something to go off for a bomb. When you still need to worry about eye safety when you haven't decided that you're going to kill something. This is an eye safety chart, which shows that you can get about 1 joule per square centimeter flux as acceptable at 1500, and you're more like a microjoule when you're at down in the visible. And this gives you an idea. Coherence length is a big deal. Let me take another drink of water here. You need, if you're doing coherent LiDAR, you need a coherence length at least twice the distance to the target, unless you delay the local oscillator. So, and this just gives you an idea. And then this is spatial coherence and temporal coherence. I hate it when somebody says lasers are coherent. You don't know anything. Is it spatially coherent? Is it temporally coherent? Unless you put an adjective in front of it, you're not really describing any specific phenomena. So, Gaussian is very nice, and these are the other, and you can get the Laguerre Gaussian modes, you can get the rectangular Hermite Gaussian modes. And lasers actually are pretty broad. When you have a 0.1 nanometer filter, you think that's really good. That's 13 gigahertz. So you compare the narrowness of a coherent LiDAR that might have 50 megahertz, 50 kilohertz, 10 hertz, as its wavelength, against the 0.1 nanometer wavelength is a huge difference. So direct detection LiDARs tend to be much broader. Now that's good from a point of view of mitigating speckle. It's bad, however, if you want to narrow and filter, discriminate between one thing and another. Some applications, driverless cars are the hottest things going right now. Actually, I like to say I made the world's youngest billionaire. And actually, he would agree. I evaluated Luminar's LiDARs 3 times and talked to their investors afterwards. The last time I did that was about a month before they went public with what they call a SPAC thing. And I gave them a clean bill of health. I talked to their investors. And Austin Russell, who was 26 at the time, became the world's youngest billionaire when the stock doubled. And he's an interesting character. I met with him when I went down and I gave a week-long course at Luminar about LiDAR. Here's what you guys should know about on LiDAR. And I went out to sort of a late dinner with him. And he said when he was 12 years old, he was doing things on the internet. And Intel effectively offered him a job without knowing he was 12 years old. They couldn't hire him because of child labor laws. But he said he did make a deal with them where he would get chips in exchange for doing things for them. They'd give him IC chips. So he did work with them. But the other thing is, I told him that I didn't really want his life because we broke at about 11 p.m. and he was going to go back to work because his flight in the morning wasn't until 6 a.m. And I said, nah, I may be type A. I'm not that type A. Okay, this is a driverless car, 360 degrees around. I really like LiDAR, but driverless cars are all about fusion. They're about LiDAR and radar and cameras and getting the best doggone answer you can. I do like to say that I don't think Elon Musk is dumb, he just lies. It's good for his stock when he says that he doesn't need no stinking LiDAR, but he's just flat wrong. And he's been saying for a while that, and one of the things I would say with that is, imagine, and this is a case where I would love to be an expert witness. Imagine, so far he's fine because he's only saying level 3. So the person is supposed to be, alert. The first guy who died in a Tesla was watching Harry Potter, and he just texted that, so they're good. But if he said level 4 or level 5 and the machine is responsible, I would love to be the expert witness in there, asking, so if you hadn't been cheap and were willing to pay for a LiDAR, would my client have died? And the answer is probably not. So to me, I think even if you don't do it from a technology point of view, you need to do it from a legal point of view. And I really do think that a LiDAR, you want to bring all the capability you want. I would like, if we get 40,000 people killed per year, I'd like 4,000 or 3,000, and humans are really good. Our processor is wonderful. You're driving along and you see a few kids playing with a ball up there. You've got to watch that. The ball might come out in the street and those kids are going to be running out. How do you train a machine about that? So I think, you know, the processing that your brain has is probably better so far than what we do, and so I think we need all the sensors we can get. And this is just showing, this is the most common auto LiDAR is the Velodyne HDL64. This just shows the elevation field of view, and you can see it goes up just a little bit, and it goes down. They've got 64 elements. Down in here, it's too close. Later on, people began to think about foveated vision, where you put more of your pixels out here where they count instead of wasting so many down in there. 3D mapping LiDAR has been around since the 90s. It was single detectors flying 3 to 6 kilofeet. Then in DoD in 2010, we put the Halo system up. Harris introduced the Geiger mode APD camera using Princeton Lightwaves cameras in 2013. You could make one using a linear mode array, but nobody has. Types of LiDAR. 1D, I'll say a little bit more about what all these are. And types of coherent. Laser vibrometers, again, I'll say more about them. This is a 1D LiDAR, where you're just doing, oops, I didn't mean to do that. You're just doing range resolution, like this. And so you see you get a return there. 1D is actually pretty doggone good for an airplane. And if you do tomographic imaging, you can actually get somewhat of a 2D. This is a 2D image. This is an image of a 8 to 12 micron FLIR. Same image with a 1 micron LiDAR. You know, if you can do much better. 3D mapping has become a big deal. This is the 911 area. And there was a group that was paid to map that area periodically to see if the rubble was shifting. This is San Francisco. Yeah, flash LiDAR means you illuminate a wide area, and you know, whereas scanning you just have a small detector. Laser vibrometry. This gives you an idea. 1 micron per second gives you 1.129 hertz at 1.5 micron, 3 times that if you go down into the visible. The other interesting thing with this is if you're doing vibration, it's going up and down, up and down. So you've got 2 frequencies to worry about. Oops, I didn't mean to do that. 2 frequencies to worry about. The frequency of the vibration and then the Doppler shift. And if you've got a bigger vibration amplitude, you get more Doppler shift in order to vibrate at a certain frequency. This is 20 years ago, a guy working for me aimed a 2 micron laser vibrometer at a transformer, and we came out at 61 hertz, not 60 hertz. But you can see, you can tell how much power is flowing through a transformer just by using a LiDAR. This was, we had in 2002, we had a laser vibrometer up on North Oscura Peak, looking out at Salinas Peak, 52 kilometers away. And you could tell if the SUV was running. You could tell if you hit the horn. You could tell if people were talking. I joked and said, can you tell if it needs a tune-up? And they said, well, of course. Every cylinder has a unique misfire characteristic. So from 30 miles away, you could tell if it needed a tune-up. Until we did this, I wasn't sure whether laser vibrometry would work well over long range through the atmosphere. And there's some people who say, well, you'll never be able to do that because of self-vibration. And my response to that is, well, the Navy will never be able to use sonar. It's essentially the same thing. But, gee, I think they are using it. We didn't do it. The Navy, actually, from Point Loma in San Diego, they would use the CO2 laser vibrometer back in the 80s, I think, and they imaged a ship going by. They made a waterfall plot, just like the waterfall plot you would get from a sonar. They handed it to a sonar reader, the sonar guy. He named the ship and said, where did you get such a clean waterfall plot? Yeah. So I think that's pretty doggone neat. LiDAR summary, rich phenomenology. I think LiDAR is going to be a big deal. The military and NASA have been doing it for decades. Actually, I didn't put in much history of LiDAR in this thing. There's a question. There's some references. As I said, there's mine there. There's a new book that's going to be coming out from Maurice Halmos that I think will be good. There's a detectors book. Greg Oshie's book is really, really good. This book by Al Jalalian is sort of old. There's a nice book that just came out. Well, it's maybe on the next one. This is Sammy Henderson wrote a 300-some page chapter in that book on atmospheric sensing. And then I was putting an ad in for this, if any of you want to listen to me for a week over Zoom or come there. And I don't know how I did it. I think I did it quicker than I needed to. I could have talked about more subjects. But so that's what I've got. I've got lots of things I could talk about, but no. Questions, comments? It looks like people have done that some before anyway. Yes?
Yeah, so thank you very much for this very nice talk. I really enjoyed it. It was also pretty funny.
Yeah.
One question. So when we had this question about the precision,
Yes.
right? Then you said something, so I do this 2 laser pulses and I can make lasers.
I'm going to sit down while you do this.
And I do this with the 2 laser pulses and I can actually make pretty narrow pulses and everything is fine. Yeah. But you did not comment so much on the detection side, right? Because you also have to make sure that your detector is good enough.
The detector has to be fast enough.
Yeah.
If the detector isn't fast enough, then you lose on that.
All right. I know that there are like a few tricks on the detection side. It would be nice if you can also like comment a little bit on that.
Well, it really has to do with the bandwidth of the detectors. Geiger mode APDs are one of the more common things now. If any light comes in, it just goes bang, and you end up getting a pulse that's big. So that's just a timing thing. You have linear mode APDs, Geiger mode APDs. It really comes down to the bandwidth of the receiver. So that you just need a bandwidth that you want to have 500 megahertz if you want to get 1 foot resolution on your detector.
Are there some continuous wave tricks that you also can?
Oh yeah, absolutely. If you do FMCW or pseudo-random code, FMCW actually, Bridger Photonics in Bozeman, they actually made a LiDAR with 26 microns of resolution, 4 terahertz bandwidth. And the way they did that was linear mode FM, and they chirped over 4 terahertz. And your detector could, and if you chirp the LO the same time as you chirp the transmitted signal, you can make sure that the beat between the two of those is within the band of the detector that you're using. So I can have a detector that's 100 megahertz and still do 4 terahertz worth of resolution, or 26 microns, by chirping the local oscillator at the same time that I chirp the other signal.
That's very impressive.
Yeah. Yes.
When you were talking about coherent versus direct detection, it seemed like it was mostly in the context of being able to do added features like vibrometry and so forth.
Yes.
But isn't there also just a huge difference in dynamic range and signal and noise?
The first time in the 80s, CO2 laser radar was the king. The detectors weren't that sensitive. They were all coherent because of sensitivity, because you can turn the local oscillator up and bury most of the noise. That was the original reason why people did heterodyne or coherent. Now, in many cases, we've got sensitive detectors, so that isn't as strong of a reason as it used to be to do that.
So it's just a design option?
It's a design option, yeah. But turning up the local oscillator is a good way to get rid of noise. Now, then you've got a strong local oscillator, and as you go to more and more, if you've got, 100 by 100, then you're turning up local oscillator in 100 pixels. So as you go to more of an image, a flash imaging thing, the power required for your local oscillator comes up. But it's an engineering trade.
I'm interested in the context of being able to get away with really small apertures, a lot of diffraction loss.
Right.
Not worry about it because I can pick up 30 dB in dynamic range with coherent.
You're going to get rid of some noise. Now, the dynamic range, there's an issue that you probably, you would like AC coupling on your detectors if you're using coherent. So I can turn up the local oscillator and I don't lose dynamic range. If I do DC coupling, I lose dynamic range when I turn up my local oscillator. So I don't know.
One other question. One of the applications that always intrigued me in the SPIE world was being able to listen to conversations using vibrometry.
Right.
It seems like relative to the example you gave, that's like falling off a log.
Oh, it is. It's easy. It's easy. And if you happen to go into classified facilities, you'll see they play music against the windows. Just so that if you want to put something against the window, that's fine. What music do you like? I'll turn the channel for you.
Just one for that.
Yes. Yes.
What are the different detector array technologies that are out there, and where do you see it going? There are CCDs and photodiode arrays, and then there are avalanche arrays, avalanche detector arrays. How do you compare these things for this application? What are the
Okay, so actually I wrote a paper that did some of that, which was a comparison paper, I forget exactly. After the National Academy of Sciences study that I chaired, it's like there's two religions. There's the Geiger mode religion and there's the linear mode religion. And they're religious zealots. That's died down somewhat now. Geiger mode, when one photon comes in or a million photons come in, bang, you get a maximum amount of signal coming out. Linear mode, it's a factor of 10. I get 10 times more photons coming out when you increase by 10 times. The nice thing about the Geiger mode is most of the noise disappears, and your readout circuit is really simple. So Geiger mode has been gaining a lot of interest in spite of the fact that it doesn't give you grayscale at all unless you do multiple returns. If you do multiple returns with Geiger mode, you can do grayscale. But so I would say Geiger mode has been doing better. For coherent, I really like linear mode rather than Geiger mode. You can do coherent with Geiger mode, but you're looking at a beat frequency, and you really would like to see the amplitude of the signals to see the beat. And when you do it with the Geiger mode, what you have to do is look at the frequency of the returns. In any event, MIT Lincoln wrote a nice paper on how to do coherent with Geiger mode APDs, but it's really a funky way to do it, and there's a real dynamic range issue. So I would say, and DRS has made essentially a photon counting linear mode detector array. The problem with that is it's in mercad telluride, and it's like $1 million, and takes a year to get it. It's very expensive. People have been trying to get high gain linear mode APDs with low noise. When they do, I think that's going to be very interesting, and I think eventually we're going to go that way, especially as we do more coherent. But people, Joe Campbell, Sanjay Krishna, have been doing work, in the area of the linear arrays that you can manufacture. Mercad, the problem with Mercad is there just isn't that much science in the material. DoD is interested in it, but silicon, the amount of money that's gone into silicon, the amount of money that's gone to indium gallium arsenide is orders of magnitude more than Mercad. And so I don't think Mercad, unless you discover some use that's going to mean somebody other than DoD puts money into it, I don't think it's ever going to be at the same level. But so you have people, though, making indium gallium arsenide linear mode detectors. Right, most of those have been 10 to 20 gain, which only gets rid of some noise. If you go up and you can get 300 to 1,000 gain, like Mercad does, or you get even 100 gain, then I think they'll be will be much more effective. So I'm expecting over the next 5 years or 10 years, people are going to get higher gain linear mode indium gallium arsenide that'll come closer to photon counting. And I think that's going to be an interesting detector as it evolves over the next 5 years. Yes?
So one thing with this automotive LiDAR and the Elon Musk discussion, right? He's saying he just wants camera and a radar, that's enough for him. He doesn't want the LiDAR. But I think for short distances, maybe that's true. But if you want to predict things that are farther away, you do need the LiDAR for sure, I think.
I actually wrote a paper touting stereo over LiDAR that I gave at the Defense and Commercial Sensing thing like 10 years ago. But that's for very short range. But the other thing about that is, look at that wall right there. Try and do stereo off that wall. The reason why Tesla, it slammed into the side of a truck. There's another truck that landed, that turned over on the freeway. And if you're doing stereo and you have a flat white surface, guess what? You can't do stereo. You need features. You need to identify features. Now, the other thing is I talked about fusion. Fusion is really important. Those people who died in Teslas would not have had to die if they did a better job on fusion. They had a radar, and the radar knew exactly how far that truck was. But for some reason, they were using the stereo camera as in priority over the radar. And the there's a video I've seen of this guy who died going into the top of a truck that had turned over. And you see, he did wake up. You see, the smoke from his tires as he slides into the truck. But he didn't discover it soon enough and get on his brakes. But so stereo is fine for short range. As you go longer, it's not so fine. And stereo doesn't work at all if you have no features. So counting on it when you have things like the side of a truck or the top of a truck out there is probably not a smart thing to do. Yes?
So I've seen with a lot of laser Doppler vibrometers, they use a sawtooth carrier. Is there any advantage over that versus like a triangle wave carrier signal?
I don't think so. I think it's about the same. Either way, one or the other. Yeah, you can use either one. The linear mode FM is a good thing to do. You can do pseudo-random code too. The nice thing about the linear mode FM, though, it's much easier to be able to go to higher bandwidth with this technique where you chirp the LO as well as chirping the signal. So, but either one of those would be fine, I think.
Okay, let's thank Paul for...
Thank you.